Thank you very much. I'm Kaushal Kafle, and I'm here to present my research on discovering flaws in Android security tools using mutation analysis. We all know that mobile apps are very useful and popular. As they say, there is an app for everything, from banking to gaming to social media to document processing and various other tasks. However, we also know that mobile apps are complex software, so they can be vulnerable and sometimes even be made intentionally malicious. As a result, the last decade or so of mobile security research has really focused on application analysis. And various tools like Maladroid, Tendroid, Flowdroid, and CryptoLint have been developed. Now, these tools focus on a variety of different tasks, from detecting SSL issues to tracking private data leaks and so on. Now, these tools are extremely beneficial to the security community as well as end users because they help to contextualize traditional program analysis techniques to mobile apps, as well as help to keep the application ecosystem clear of malicious and vulnerable apps. So these are quality tools, and they are extremely valuable. That said, let's take a step back and ask a key question. Do we really know how well these tools work? Unsurprisingly, we are not the only ones asking this question. In 2015, a group of program analysis and security experts discussed the soundness of these tools in the SOUNDNESS manifesto. The general idea is this. Static analysis tools are expected to be sound, but in order to be practical, that is to be precise, as well as finish in time, they have to make, they choose to not handle certain language features like dynamic code loading or Java reflection. This means that these tools have a sound core with all the right decisions, as well as some unsound assumptions. These tools are not sound, but they are soundy. The problem, though, is not that these tools are soundy. The problem is that these unsound assumptions might not be known outside a group of experts in that area. For a variety of different reasons. Tool developers may have failed to document them. They might have even made these assumptions implicitly, or they may even have inherited these problems from prior work without their knowledge. The SOUNDINESS manifesto calls for the documentation of these unsound assumptions, and so do we. We also want to discover and document these unsound assumptions, but there is a key difference. While the SOUNDINESS manifesto mainly concerns itself with language features, we contextualize soundiness to the security domain by developing so we contextualize soundiness to the Android platform. Now this is important because Android security tools are built for Android, so naturally they have to account for these abstractions. Like application models, the intercomponent communication, asynchronous communication, and so on. So using this expanded definition of soundiness, our objective is to systematically discover and document as many unsound decisions as we can so that we can improve these already valuable tools. So our vision is of a framework that enables systematic evaluation of existing security tools to identify and document unsound decisions so that we can eventually expand the sound core. With such frameworks, researchers would be able to discover undocumented flaws. Developers would be able to build more secure tools by fixing those flaws, eventually benefiting the end users themselves as well. With this, I present MUSE, short for Mutation-based Soundiness Evaluation, which is a framework that enables a systematic way to discover flaws in security tools and realizes a major part of our vision. To do this, MUSE uses mutation analysis, which is a well-grounded technique, especially used in software testing. But MUSE contextualizes mutation analysis to the security domain by generating abstractions, by developing abstractions in the form of security operators and mutation schemes. Let's first briefly discuss mutation analysis. Mutation analysis consists of a mutation engine, which takes applications as input and makes a small, specific, and strategic changes to it, and generates a set of mutants of that application. Those small changes are the mutation operators, which represent flaws, faults that test suites are designed to catch. So the test suite is run against these mutants. The mutants that are caught by the test suite are said to be killed. But in order to correctly assess the quality of that test suite, we are mainly concerned with the unkilled mutants, because those are the mutants that represent the faults that are not caught by the tool. So likewise in Muse, we start off with a security tool with a sound core, and we test this tool against a set of apps. In our case, these apps are going to be mutants that are generated by Muse with the help of security operators and mutation schemes. So we analyze the uncaught mutants to discover flaws in that security tool. The mutation process in here is guided by security operators and mutation schemes. Security operators are the anomalies or the faults that are inserted in the application. But just having these anomalies to insert is not enough, though. They have to be inserted at strategic locations to maximize their effectiveness. Therefore, we use different mutation schemes to place them in specific places and scenarios for expressive mutation seeding. So now that we know about these abstractions, let's dig a bit deeper. So while designing the security operators, our goal was to encompass as many tools as possible. But that soon proved to be challenging. If we made the operators too fine-grained, that is one operator per tool, our approach would not be scalable. Alternately, generic operators that are designed for all the tools at once was not effective, because different tools have different security goals. So we addressed this challenge in Muse by striking a balance. We define security operators in terms of security goals. So this approach is both scalable as well as effective, because security operators that are defined for one tool applies to all the other tools that have the same particular security goal. Here are a couple of examples of operators for different types of tools. So the first one is for data leak detection tools, where we extract private user data and leak it in the form of a log. So tools that are made to detect data leaks should be able to detect such a simple instance of a leak. Similarly, the second example is for tools that detect SSL issues. Here we modify the isServerTrusted method to always return true. So the trust manager simply trusts all the certificates. So these are just two of the many examples of operators that we can use with Muse. But to make them effective, we use three different types of mutation schemes: reachability analysis, Android abstractions, security goals of the tools. So with the first scheme, we use Muse to test the tool's reachability. This analysis sort of works as a baseline to evaluate the coverage of the tool. For this, we simply place the operator at the start of every method. While the strategy of placement itself is simple, this scheme is pretty important. We test if the tool kills all the mutants in the scenario to look for its coverage issues. So a big focus of Muse is to evaluate tools based on the target platform. So we also model mutants that are specific to Android by considering these abstractions: the activity and fragment lifecycle, callbacks, intent messages, as well as Android XML resource files. So a simple example of why we found such a scheme necessary. We placed a leak inside the onReceive method of a dynamically created broadcast receiver. And we found that this leak was detected by all of the prominent tools that we tested against. But when we placed this broadcast receiver inside the onReceive method of another dynamically created broadcast receiver, many of the prominent tools failed to detect this leak. So it was important to consider such abstractions to truly assess security tools that are built for Android. Finally, we also there are also schemes based on the security goal of the tool that we are analyzing. This helps Muse to generate mutants that are model for a specific class of tools. For example, one of the schemes for data leak detection tools is the chain-based operator placement. So consider one instance of this scheme. So we extract the private user data on the onStart method, and we leak this information in the onResume method. We know that the onResume method always executes after onStart method. So any tool that wants to detect such a leak would also have to account for this ordering. So this placement sort of tests the tool's ability to identify leaks in asynchronous ordering of callbacks. So now that we have discussed the design, let's move on to the implementation. So our implementation can be sort of divided into three different phases. First, we specify the security operators and mutation schemes using the Android abstractions and security goals. We use a mutation engine and use these specifications to generate a set of mutants. So these mutants are tested against the test suite test tool that we are analyzing, and we manually analyze all the on-kill mutants from this setup. So while this pipeline itself was effective, we found early on that a number of on-kill mutants were false positives. That is, they did not execute. So we introduced an execution engine to filter out these non-executing mutants. So this not only reduced the number of mutants that we would later analyze, this also guaranteed that all the mutants that we analyzed would actually be true positives, that they actually would execute. So here are some numbers from our implementation. So using this execution engine, we were able to reduce the number of mutants from 7,584 to 2,026. So we evaluated the effectiveness of our implementation of Muse using a case study. And we chose data leak detection as the security goal for our case study because this is one of the popular security goals for which tools have been developed. So we used 7 open source apps to generate 7,584 mutants, out of which we verified 2,026 as executable. We analyzed 3 prominent data leak detection tools against these mutants. And we found that none of them were able to detect all of the leaks. So to do a deeper analysis, we chose flawed mainly because of its impact. It has been cited over 900 times, and also because flawed is actively being maintained. So we analyzed the on-kill mutants, and we discovered 13 different flaws in flawed. So these flaws we classified into 4 different categories based on why these flaws occurred. So these are missing callbacks, missing implicit calls, incorrect modeling of anonymous classes, and incorrect modeling of asynchronous methods. So in the interest of time, I would like to point you to our paper where we discuss all of these in detail. So while finding these flaws was was a part of our objective, we also wanted to explore whether these flaws propagated from one tool to another. So we did a flaw propagation study. The table here represents 6 different tools, along with 3 different versions of FlowDroid, which were released during our study. And so we tested the 13 flaws. We generated minimal APKs for the 13 flaws we found in FlowDroid, and we run those APKs against all of these tools. The cross represents the failure of the tool to detect these flaws. So to summarize the results, we found that the tools that inherited FlowDroid as a black box, perhaps unsurprisingly, inherited all of these flaws as well. The tools that were motivated by FlowDroid's design but made some tweaks and changes to their own implementation inherited these flaws partially, around 50%. The tools that had the same security goal but had their own methodologies were the least impacted by this flaw propagation problem. So this does not, however, mean that one tool is better than the other. Analyzing another tool, the uncut mutants from another tool, might have given us different results. So if you recall, the end goal of our vision was the expansion of the sound core. So, and we fixed one of the problems that we discovered in FLAW that would have been harder to manually find. However, we also discovered that many of these flaws were actually unresolved design and research challenges that are hard to fix, and they would require and they are actually they could be potential targets for future research. That said, Muse facilitates an effective a systematic way to discover these flaws so that they can be better documented and targeted by future research. So while Muse itself is effective, there are certain caveats. Muse does not claim soundness, as we have acknowledged in the paper as well. As a result, we don't seek to replace formal verification techniques. However, Muse does systematically discover unsound choices in sounded tools. So it offers a significant advancement over manually curated benchmarking tools. So in conclusion, we demonstrate with Muse the effectiveness of mutation analysis to discover flaws in security tools. Additionally, we also discover that flaws exist. They not only exist in a single tool, but they actually propagate from one tool to another, which makes it doubly important to actually document these flaws in proper channels. Further, Android and its ecosystem of apps and tools are constantly evolving. And Muse can help researchers keep up with this evolution much better than manually curated benchmarking tools. Finally, fixing flaws is a hard problem that needs future research. But identifying and documenting them properly is an important first step, which is where we hope that Muse can be most effective and useful. With this, I end my talk, and I'll be happy to take questions.
Okay, thank you. And again, we have time for some questions. There are no questions. I have at least one. So it seems like in your evaluation, DroidSafe and some other tools, they didn't discover that many flaws. Do you have any intuition why those tools are or look a bit more soundy than others?
So during just so that I can understand the question properly, are you talking about the table at the beginning where we?
No, the later table where you had the case study. If you can just go, I think 3 slides back.
Let me.
Yeah, this one.
This one?
This one. So DroidSafe and also Blue Seal seem to be more precise in the sense that they covered or they were not affected by the output of Muse.
So the flaws that we have here, we analyzed. So we discovered from the analysis of the mutants that were not detected by FLAW. So these are representative of the flaws that we discovered in FLAW. So in order for us to correctly assess the quality of another tool, we would have to actually manually analyze the uncut mutants from that tool. So it is not reflective of whether one tool is better than the other. It is simply reflective. So this table here is reflective of the fact that tools with similar security goals, if the flaws are not known to the wider community, they might propagate from one tool to another. So this table here is representative of that fact, rather than the fact that one tool is better than the other.
Okay, thank you. And then the other question was the input for your tool. How does this look like? So is it a human analyst that needs to write the test cases that are then mutated, or what kind of expert knowledge is needed to come up with other, let's say, corner cases?
So there are 3 mutation schemes that we use with Muse, and slight domain knowledge is indeed required to in at least 2 of those cases where we use mutation scheme for Android abstractions and mutation schemes for security goals. So there is certain familiarity that is required with both of those domains, and we curate the security operators and the placement of those security operators based on that.
Okay, thank you. So if there are no more questions, then we end the session. We now have the lunch break, and yeah, thank you for being here.